Hi, in this video I want to explore two-source interference, which is yet another interference effect, and one that you're also going to explore, or maybe already have explored in the lab. So here's the picture. I've imagined I've got two sources for my waves. They could be anything. Maybe there are two speakers that emit a single tone of a single fixed frequency, or maybe this is a pool of water and there are two little things going up and down, creating waves at regular intervals. Or maybe there are two light sources. So whatever they are, they create the same waves. Right? We assume they're set to create the same frequency, therefore the same wavelength, waves the same speed, and so on. And let's make the additional assumption for now that they're creating waves at the same, like in phase with each other, right? So right now, the way I've drawn it here, they're both creating a wave crest, right? So these lines, they're the wave crests. In this case, these ones, those are bluish ones, the wave crests produced by this source. The green ones are the wave crests produced by this source. And they're spreading out outwards, right? Should be fairly clear. Now, what you notice, there'll be areas where there's a crest on a crest, right? So for example, here, and here, and here. In those areas, the crests are going to build up and the waves are going to be extra high, right? They interfere, principle of superposition. So in those areas, we talk about constructive interference. Because the waves, they build up on top of each other, right? So I'm going to put a big, I'm going to label this, I put little C's where there's constructive interference. So they'll put a big C right here, a C right here, a C right here, right? Because there's a crest on a crest. It's making a higher crest. In fact, you can easily see that if you have a pool of water, you can just put your finger, so you have a tub of water, fill it with a little bit of water, you stick your finger in two places, do this at the same time, you can see this kind of effect. Now, those waves, they move, right? This is a static picture that I took at one instant. A little bit later, the green waves have spread out. So this one would have sort of moved to here, say. This one would have moved to here, say. And then I'd get a crest on a crest here, for example. Right? If you imagine those waves spreading out. I'll show you a simulation in a second. Right now, here, there's a trough of the green ones, but it's right in the middle between those two green ones. There's a trough from the blue ones, because it's right in the middle between those two blue ones. So here, there is trough on trough, which makes a trough extra deep. So there's also constructive interference, right? Because they build on each other. Same thing here, 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 right? Whereas you've got not only where you've got crest on crest, but also you've got a trough on a trough. And the wave troughs are halfway between the crests. The crests are marked. And we could mark those troughs maybe with a sort of dashed line like this, and there would be a trough here, and there would also be a trough here, like halfway between the crests. And so you can easily see that where you've got trough on trough, right in the middle of those not squares, those skewed rectangles, here we get constructive interference as well, right? All right, so then I could imagine if I'm just in front of the wave, say here, right? Just in front of this one, just in front of this one, maybe a quarter of a wave cycle. Again, they're in the same spots. If I wait just a little bit, this one will move to here, this one will move to here, and again, I can see that the waves here, they work together to build up. So I get this whole line of constructive interference. And if I'd done this more carefully, this should be a straight line. Right? Because in all those spots, whether there is a crest or trough right now doesn't matter. If I know, okay, right here there will be a crest on crest in just a second, they are in phase, we get build up right there. Right? And this, maybe I'll do another one sort of line here. As long as they're in phase. Again, this should be a straight line if I drawn it right. Now, There are other areas where I've got a crest on a trough. For example, here, right? Take this point here. There I've got the green one has a crest, the blue one has a trough. So they're going to cancel out. So destructive. So constructive was e.g. crest on crest, or trough on trough, or somewhere in between, on the same spot somewhere in between. Like both sources are the same place in the wave cycle have constructive interference. If they're on opposite sides of the wave cycle, I have destructive interference. So e.g. crest on trough, doesn't matter which way around, or one going up while the other's coming down at the same time, so they're constantly doing this, right? Imagine those are two waves. You'll see what I'm trying to do here, like this, right? If one wave is doing this, the other one's doing this, but out of sync like that, they're always going to cancel out. Whereas if they're at a point where they're doing this, they'll always build up and work together. So this, for example, is this destructive. This is a crest, this is a trough, so right here there's nothing. These points here. So you can tell you get this pattern where I've got one crest, one trough, one crest, one trough. You get sort of lines of destructive versus constructive interference. And I call the lines of destructive interference, I'm going to give them the name nodal lines. This is just terminology. Lines of destructive interference. We call them nodal lines, and you know the term node from the 0 points for a standing wave. Right there you've met the term before. In this case, we've got whole lines where there is destructive interference, because we're now in a 2D scenario, or maybe even a 3D scenario. If those waves were spreading out upwards and downwards as well, of course, I can't draw that, but sound waves would do that, light would do that. Water waves would look more like this, flat on a sheet of paper. Alright, let's figure out with a numerical example where I expect to find constructive and destructive interference. So here's my first setup that I want to analyze. I imagine I've got two sources, 1 and 2 here, and I imagine they're 4 meters apart. I'm interested in the point that is 3 meters in front of source 1. So maybe those are two speakers, they emit a single note, single sinusoidal wave, and I'm interested what happens at this point here. Well, it depends on the wavelength. Let's suppose my wavelength is 2 meters. Right. So what that means is if the wavelength is 2 meters, then there's 1.5 wave cycles between here and here. Right. What about this distance here? Like this distance here from the other speaker. Well, by the Pythagorean theorem, if this is a right angle triangle, which it is because this is right in front of 1, right? 3 meters, 4 meters, 3 squared plus 4 squared, it's 25. Root of 25 makes this 5 meters. So we figured that one out from the geometry. So that means this speaker here, because the wavelength is still 2 meters, it's going to be 2.5 wave cycles, right? So if I plot that with the blue and green colors again, if I imagine right now this one's emitting a wavefront, and the last one was emitted such that this distance is 2 meters, right? And so this is going to be a trough here, and this is going to be right on a trough. Whereas this one here, I'd have I'm going to eyeball this. Right now it's producing 2 meters, 2 meters. Again, I of course didn't draw this quite perfectly. And then this is again going to be on a wave trough. Right here, the troughs, because it's 5 meters. So crest after 2, crest after 4. Next crest would be at 6, but the trough is right there. So it's trough on trough. So it's constructive. Right. So what do I have? I've got that R from 1, so the distance, call it R, right, from point 1 to A, that would be 3 meters, which in this case is 1.5 wavelengths. Distance from 2 is 5 meters, which is 2.5 wavelengths. Right? But it means because they're both at the halfway point in their cycle, they're in the same cycle, right? The wave that arrives here, that trough, was emitted before the trough from 1, because it had to go further. Right? So it's not the waves that meet here weren't produced at the same time. The crests or troughs that meet here weren't produced at the same time. But because it's both 0.5, right, they're in the same place in their cycle. So both 0.5, so at same point in their cycle. Right, so that means they interfere constructively. Constructive interference. Let's do another example. Let's stick with point A, but let's change the wavelength. Right? So let's say, what about lambda equals, how about we make it shorter to 1 meter? Shorter wavelengths. Well then, right, I have 3 full cycles from here to here, and I've got 5 full cycles from here to here. So I've got R1 equals 3 meters, it's now 3 lambda. R2 equals 5 meters, so 3.0, right, equals 5 lambda. So now they both have 0.0, so exactly both a full number of cycles, so they're both, in this case they'd both be wave crests if right now a wave crest is emitted. If right now a trough is emitted, well, then they're both troughs, because the whole number of wave cycles from here to here. 0.0, so again, constructive. Right. All right, let's do, I should tell you a second way of doing this. Alternatively, instead of just looking at how many wave cycles is it for each one and comparing those, I could just look at the difference in path. So another way to do this, or another way to calculate this, is the path difference, right? R2 minus R1 is 2 meters, which is it's a whole number of wavelengths, exactly 1 in this case, whole number of wavelengths, so that implies that they again, they must be in the same part of their cycle. So I guess this sort of again leads to this conclusion here. So 2 ways to come to the same conclusion, the same point in their cycle. One is, look, they're both at a halfway point between for a full cycle, right? They're both at, if the full number here is crest, 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 they're both at a halfway point, meaning a trough. Or I can just say, look, if I look at the difference in the path length, that's the whole number of wavelengths, so they exactly, the phase difference between them is exactly a full number of cycles, in this case 1 full cycle of going up and down. Right? But 1 full cycle, meaning they're both going up and down at the same time, it's just one is a whole cycle behind, but you can't see that, of course. And then here, right, again, both are 0.0, so again, constructive, or I could say lambda is equal to, R2 minus R1 is equal to 2 meters as before, which is again a whole number of wavelengths. In this case 2, because lambda is 1 meter. That's an example where they're not constructive, right? So we're going to stick with this one again. Let's though pick different values. Let's suppose lambda is equal to 4 meters, so 4.0 meters, making our wave significantly longer now. So what do I have then? Here's my question. Now what happens then? Well, R1 equals 3 meters equals, let me write like this, 0.75 wavelengths. Right, because a wavelength is 4 meters, a wavelength would be from here to somewhere like here. So it's only 0.75 wavelengths from the speaker or from the source to the point A. R2 is 5 meters, which is 1.25 wavelengths, right? So the fraction of the cycle they're on, it's not the same. They're half a cycle apart. That means they're in opposite sides of the cycle. Opposite points in their cycle. Right, so for example, it could be that this one here is right here, and this one here might be right there. Then you add them, they'll add up to 0, and 1 second later it could be that this one here is here, and this one here would be here, right, in their cycle. But this plus this plus this point plus this point, this point plus this point, they're always opposites. It's not going to change because, I mean, the path difference between them is the same. So this one will always be a half a wavelength, in a sense, higher than this one. Right? There's a difference in path is always the same. It means it always will be half a cycle away from the other one, which means they'll always interfere destructively. Destructive interference. What about this another one? And we're going to stick with point A still, right? Let's say it's 3 meters. Well, then R1 is exactly, so it's 3 meters, which is 1 wavelength. R2 is 5 meters, which is 1.67 wavelengths, or 5/3. So they're not exactly opposite. So it would be 1/3 of a cycle apart. I guess technically it's put 2/3, but be 1/3 to the next full cycle. Kind of the same thing, as it turns out. 2/3 of a cycle apart. So not quite on opposite points, but kind of closer. So say it's mostly destructive, but not perfectly. Oh, but not completely. So what would you see, or what would you hear? You'd see very small oscillations, but you'd see something. Whereas here you'd see no oscillations at all. You wouldn't hear anything if those were speakers, right? Then the sound would just interfere, and you wouldn't hear anything. Kind of how, say, noise-canceling headphones ultimately work. Same principle. So here we get mostly cancellation, but not completely, because they're not exactly on opposite sides, right? So one of them, one of them might be here, and then the other one might be sort of here. So it's not right at the bottom. It doesn't cancel out completely, but it's sort of negative. It opposes this, but it doesn't cancel out all the way. Now, if you understand that idea, right, then you can deal with those kinds of situations and answer all sorts of questions, right? And you do get some practice doing that in the lab and the homework as well. Now, let's write down a general rule, right? So we're asking, is the path length difference equal to, now what are our options? A whole number of wavelengths, a like halfway between a whole number of wavelengths, so halfway between whole numbers of wavelengths. So that would be e.g. half lambda, 3/2 lambda, 5/2 lambda, and so on. That's another option. Or is it somewhere in between? It's neither so it's neither lambda or 2 lambda or 3 lambda, right? But somewhere in between. Well, in each case, we're going to get a different outcome. In the case of a whole number of wavelengths, that means it's going to be constructive. Why? Because even if the point that we're looking at isn't the same distance from the two sources, right? Even if it's further from one than the other, the waves that arrive from each source, they're in the same part of the cycle. It's just one might have done 5 oscillations since it's come from the source. The other one might have made 7 oscillations since it's come from the source. But they're both crests at the same time and troughs at the same time. Right? Whereas if it's halfway, that means they're like half a cycle apart, 1.5 cycle apart, 2.5 cycles apart. Either way, they're going to be on opposite sides of the cycle, so they're going to cancel out. Somewhere in between, well, then it might be partially constructive, destructive. And, in most spots will be somewhere in between, but it's easier to sort of keep track of where those are. So that's pretty much it. The rest is applications. Now there are of course some special cases we could consider. For example, let me just go back to my picture here. Instead of point A, right, we might have had any other point, but if we're somewhere along the middle line, right, the line in the middle between the two sources, there of course it's always going to be constructive because it's the same distance from both, so you're going to be in the same point in the cycle, assuming the sources create their waves simultaneously, right? Like they're in sync with each other, they're in phase with each other. Another interesting areas to look at is just left and right, or like or somewhere between them, like along this line here, that's in the line of the sources. Because anywhere along that line, right, the path length difference is the same. It's just the distance between those two, right? This point is always 4 meters further from 1 than 2. This point is 4 meters further from 1 than 2. Right? So anywhere along the line, it's going to have the same type of interference. Constructive or destructive, well, it depends on how the 4 meter relates to the wavelength. Anywhere else here, right, it really depends on geometry. You have to take this distance, like a direct distance in a straight line, and then you ask about the path length difference between this and this, right? Or you work out the number of wavelengths for this one and this one, sort of compare the cycles like that. Ultimately, you're doing mathematically the same thing. I just wanted to show this to you on a simulation. So let me pull that up for you. Alright, so here's another one of the Phys simulation from the University of Colorado. And in this one I imagine I've got a pool of water in this beautiful blue color. And I've got 2 pipes and they're going to drip water droplets. Right, so I'm going to turn them on. Let me do that. I guess I'll just push the button here. So when it drips, you can see the waves spreading out. Now in this case, I guess I imagine that the black one is a trough, the blue one is a crest, or vice versa, it doesn't really matter, right? But we imagine the black one is a trough, the blue one is a crest, and you can see them spreading outwards in a circular pattern. Now I'm going to turn on the other one as well, right? Let's wait a bit for the waves to spread out, and I'm going to pause it. They're in sync, the drops are falling in the same time. Okay, let's pause this and have a look. So what you can see here, remember, black is crest, black is a trough, blue is crest, right? It's really a tall wave, really, low down valley in the wave. you notice is the waves are big along the center line here, and they're big over here, but along the sort of lines here, it's just this sort of intermediate gray. What does it mean? Well, that means here the water doesn't go up and down very much at all. So those would be our nodal lines, right? Because they're the waves that arrive from here and from here, they meet here, but because of the path length difference from here, let me show this to you. So here, right, say take this point here, how do I do this? Right, from here it would be 4.5 centimeters to this point here. From here, I have to find the same point again, I'm going to be rough, it's 5.5 centimeters. Right. Now, if what's the wavelength? The wavelength is going to be, we can measure this too. I guess where can I do this? Right here. Right, the wavelength, this is one wavelength, is about 2.6, 2.5, something like that. I'm being very rough here. So this point here is fairly well, and I have been rough, right, fairly well, the path length difference, excuse me, is 1 centimeter, which is, you know, fairly close to half of one wavelength. So this is going to be a destructive area. If I were very careful, I would find the exact line where the path length difference from here to that point and from here to that point is exactly half a wavelength, and that gives me that nodal line. Now what I can do too is I can change the, I can make them drop a bit faster. Let's see what happens then. Let me just reset this. So I'm going to do this, and I will do this. So we'll wait for it. This one had a head start, right? And we can see if I make the frequency higher, therefore I make the wavelength shorter, because frequency times wavelength is wave speed, and the wave speed stays constant. You can tell that the pattern sort of becomes more pronounced, it becomes more condensed, or it's closer together. And if I make it even more so, let's just wait a bit for the waves to spread out. You can see I now get a second set of nodal lines here and here. Right, so constructive, destructive. Constructive, up, down, really high, really high ups, really low downs, right? As here, pretty much the same water level the whole time, because the waves from here and the waves from here, they destroy each other along those lines. And we just did a calculation with the geometry. The other thing I can change the separation. Let's make it really far apart. Let's see what happens then. So you can now see, moving really far apart, a lot more nodal lines, right? And that's just from the geometry. A bigger distance apart means it's easier to find points that have significant path length differences from one to the other. Right, conversely, I can move really close together, and then I'm getting this. Let's have a look. So I can just about see one nodal line here, one nodal line down here. If I make the frequency lower, so I'm making the wavelengths a lot greater, you can tell now I can't see very much at all. Why not? Well, I've made the wavelength, in this case, significantly longer. Right, the wavelength is from here to here. It's significantly longer than the separation between the sources, and so it's hard to find points where they're more than, say, half a wavelength apart. The path difference is more than half a wavelength, right? In fact, if those two sources are less than half a wavelength apart, then you're not going to find any point anywhere that has half a wavelength path difference. It's just geometrically impossible. And so in this case, you don't get very much visible interference. You get a little bit, but only a little bit of partial destructive interference. Mostly, they're very close to being in sync. So almost everywhere, it's constructively interfering, almost as if I had a single source. So you can play with the simulation, you can play with the geometry. There are also other versions. For example, I can just look at, this is a single wave. I can use light, and again that's something we'll be looking at in another lab. You might be doing with two slits to simulate a sort of two-slit light interference, which is a another very interesting phenomenon you'll be studying. That's essentially a version of what we just looked at. But most of the calculation you're doing in a situation like this is ultimately geometry. Right? To understand the underlying principle, compare the phase of the two waves that arrive at a point. Are they in the same part of the cycle? Are they in different parts of the cycle? If you can understand that, and then the rest is geometry, you can work it out. Is it constructive? Is it destructive interference? How many nodal lines are there? And so on. Ultimately, all just a matter of geometry once you've got the basic principle down. Alright, that's all I'm going to say about it. The rest is practice.